Welcome to the second installment of the lecture on the geometry of the screen, in which we'll be talking about 3D graphics. But even before that, we have to start from the Thales theorem, or Thales theorem to use more Greek-sounding pronunciation. You may know this theorem as an intercept theorem, because it's all about two intercepting lines that are additionally intercepted by a pair of parallels. And another name of this theorem is basic proportionality theorem, because it's all about the ratios or proportionality between various line segments created by these intercepting lines. And yet another name for this theorem is the similar triangles theorem, because these lines have created two similar triangles, a bigger one, ABC, and a smaller one, ADE. Similar triangles are triangles that have been created, or one of them have been created by scaling the other one. So they only differ by the proportion or proportionality or scaling factor. So they will have all the angles identical, and they will only differ with the length of the edges. And this theorem is actually about the proportions of the edges of these two similar triangles. For example, the AD edge over AE edge, so this kind of a proportion in the smaller triangle, is equal to the proportion between this segment here, DB, and this segment here, EC, and also the longer segment AB here and AC here. These are not the only proportion in this theorem. Actually, nearly every pair of corresponding edges will be proportional. You can create a proportionality equation on this basis. I think you feel what it is about. If so, we can go ahead to more interesting stuff. Okay, so perspective projection in 3D, or how to display a 3D image on a two-dimensional computer screen. So first of all, as you can see in this picture, apart from x, y coordinates, we now introduce the z coordinate, which goes inside the screen. This is a coordinate system typically used in 3D solutions. It's similar to what we had in 2D. So there is the x-axis running across the screen along its length, and the y-axis going from the bottom to the top. The main difference is that the center of this coordinate system is somewhere here, somewhere in the center of the screen. And this is where the system is intercepted by the third axis, the z-axis, which on this picture here, it's already a perspectivistic projection of the z-axis. The real z is running from your side of the screen, which is somewhere over there, through my head, and goes from the back of my head to the depth of the screen. Okay, looking at this picture, any point in this 3D space has to be now projected into three different axes, x, y, and z. So the coordinates will be depicted like this. But of course, the final result of any 3D visualization is casting the 3D world onto the surface of a 2D screen. And the screen doesn't have to have any more dimensions than just two. So actually, looking at a 3D scene through a two-dimensional screen is a little bit like looking at a beautiful world outside through a window. And this window is a metaphor of a computer screen. To explain the perspective projection in 3D, I will use this sideways view. We have two axes here. The y-axis is our usual vertical axis showing the top direction or bottom top direction of the screen. But the other axis here is the z1, so it's pointing beyond the screen into the depth of the virtual space. As I mentioned, it's a sideways view. So our observation point is somewhere here next to the 0, 0, 0, the origin of the coordinate system, and we are looking at a object located somewhere in the virtual space behind the screen. So the screen is somewhere between the observer and the observed object. So that's our configuration, looking from the side, the observer, the screen, the observed object. Now we can try to draw some coordinates. So first of all, the height of this observed object is shown here as the value of y. So this y is the coordinate of the top point of this rocket in the virtual space. And the z coordinate, it's basically the distance from the observer to the observed object. That's the z. And with these coordinates, we can now write the first part of our proportion based on the Thales or proportion theorem, y over z. So y is the height of this rocket and z is the distance from the observer. You might ask, okay, this formula is relevant for similar triangles, for example, where is a triangle? Well, triangle is right here. Okay, so if we draw a line connecting the observer and the point, in this case, this is the top point of the rocket, the point we are looking at in the virtual space, we now have these two similar triangles, the large triangle with the rocket with the real object at one of its sides, and the small triangle built on the surface of the screen. And part of this small triangle is our image. Please note that a corresponding point of the image, it will be on the line connecting the eye and the the virtual point in the virtual space. So this is how this projection on the screen works. But now we can also display the coordinates of the image point. So that's not the real point, it's the image point. The height of the image, or the coordinate, the y coordinate of the top point of this rocket image on the screen will be y dash. The other coordinate, the z coordinate, we will call here f. Why not z dash or anything like this? F, if you are an enthusiast of photography, you will know about the focal distance. This value here has its name, and the name is the focal distance. If you increase the focal distance, it's what you know in conventional photography as zoom. Okay, and with a short focal distance, you get a wide angle image. So this is a important value in 3D rendering, the focal distance, the distance between the eye and the screen. With this information, we can now write the second part of this proportion, that's y dash over f. Y dash over f. So this proportion is based on the two triangles, the big triangle and the small triangle. And that's it. That's the maths we needed, because to render the 3D image, if we have a 3D model like this one provided, then for each point of the model for which you will know the coordinates x, y, and z, you need to find the coordinates on the screen, and this coordinate is y dash. So y dash is f over z y. And very similarly to this, I will not draw a special image for this, just believe me. For the x coordinate, the formula is very similar, x dash equals f over z times x. So these two formulas create the perspective projection for any point with x, y, z coordinates in the 3D space. You can create a projection on the screen with the coordinates x dash and y dash at the focal length f. Now, please note that the z-coordinate of the 3D image is here and here. Therefore, the farther the object is from the screen or from the observer, the bigger value of z, and therefore x prime and y prime will be lower. So the image of the distant objects will be smaller and the image of the closer objects will be larger, which is exactly what we call and what we intuitively feel as the 3D perspective. So how about a practical programming example? First of all, we create an array of 3D vertices. This array contains 8 vertices forming a cube in the virtual 3D space. Each individual vertex or set of coordinates is represented by a three-dimensional vector object and contains coordinates x, y, z. So you can see that our cube extends from negative 500 to positive 500 in the x direction, so horizontally, from negative 5 to positive 500 vertically in the y direction, and also from 1000 to 2000 pixels in the z direction, so behind the screen, the depth of the screen. We also define the focal length f as 600. We'll write our program using GFC, a graphics library that either you already know or you are about to learn it, and it's primarily used for 2D graphics, but this is just a very simple example, so it's not very complex to get some elements of 3D graphics. GFC provides a special function called onDraw, which is called each time the library, the framework, needs to draw our graphics on the screen. So in this function, we first of all create a C++ for loop or iteration, which will iterate through all 8 elements of the vertices array. So this iteration, whatever we put here inside these braces, will be executed 8 times, once per each of 8 vertices in our cube, and each time the variable v, which is a three-dimensional vector, this variable v will get the value of one consecutive vertex. So for each of these vertices, we will first of all calculate its 3D perspective projection as a PRJ variable of the type C vector. C vector is a two-dimensional vector. Of course, perspective projection is about converting the 3D structure to a 2D image. So our projection must be two-dimensional. We just will calculate x and y. For calculating x in this case, we use the formula that's been just shown in one of the previous slides. So the x coordinate, or to be more precise, the mx member variable of the v vector, is here multiplied by the focal length f and divided by the z coordinate or mz member variable of the vector v. And a similar calculation we apply for the y coordinate, getting the complete xy coordinate for this projected point. The next and the final step for this example is to call a set pixel function that is called for the G object or the graphics object, which is used in the GFC library to display any graphics on screen. Our set pixel function needs to know the coordinates of the pixel we want to display. So this is PRJ, sorry, our 3D projection, and the color green. And the result will display on the left side of the screen. So we now have 8 pixels. They may be not very well visible because we only switch 8 single pixels on the screen, so they are really tiny. But here I have magnified these pixels for you, and you can now see these 4 pixels, or magnified pixels, form the rear wall of the cube. This is the front wall of the cube. But of course 3D graphics consisting just of pixels is not the most effective. Let's improve this program by adding an array of 12 edges of the cube. I hope you realize that each cube has exactly 12 edges, and each of these edges is represented by a short array consisting of just 2 unsigned values. For example, 0 and 1 means an edge connecting the vertex 0 with vertex 1. Then we have connection between the vertex 1 and 2, 2 and 3, 3 and 0. So that's going back to here, because we have to create a square shape of a cube's wall. Consecutive items are 4 to 5, 5 to 6, 6 to 7, and 7 to 4. And this edge is 0 to 4, 0 to 4, then 1, 5, 2, 6, 3, 7. These are the 4 edges on the sideway walls of the cube. Altogether, we have an array of 2-dimensional arrays. So this data structure is an array of arrays, which we sometimes call a 2-dimensional array, but don't worry about it. It's just an array of arrays. Let's make some space, okay, to write the program. So once again, we have the onRow function and a C++ for iteration, but this time it will iterate through all these edges. So this iteration will run 12 times, once per each edge, and in each iteration this variable edge will point to one of those short 2-element arrays representing the edge. In the first step within the iteration, we will unpack the edge by storing the 2 consecutive elements of the small edge array as variables i1 and i2. i1 and i2 are indices for the vertices. So i1 is the index of the first vertex, i2 is the index of the second vertex from the array of vertices. So the next step here, we will extract the v1 vertex from vertices array at the index i1, and similarly v2 vertex at the position i2. These 2 vertices form 2 ends of an edge, but before we draw the edge, we have to calculate the 3D projection, and here they are. The first projection, and quite a familiar formula for x and y, and the second projection, same formula for the vertex number 2. Now we have 2 projected points, PRJ1 and PRJ2. Time to call the GFC graphics function for drawing a line, which is not surprisingly called drawLine. We have to provide the coordinates of one end, PRJ1, and the other one, PRJ2, plus the color of the line, which is green. This will be repeated 12 times, and the result is here. This looks much more like a 3-dimensional cube, but we still have a space here for improvement. One small thing. Okay, I will add another variable, a three-dimensional vector OBS, or observation point. These are the coordinates of the point at which we are looking at this cube. Initially, these coordinates will be 0, 0, 0, and our graphics algorithm is only modified by subtracting the OBS from both vertices. So all the vertices will be moved by this OBS three-dimensional coordinates. And I will also use another standard function in GFC library, the function called onUpdate, which is called quite often by the framework. And in this function we will check for the keyboard keys WASD and additionally Q and E. And for example, when the A key is pressed, then the X coordinate of our observation point will be moved to the left by 10. 10 is the speed of this movement. D will move to the right, S will move backwards, W will move forwards, Q and A up and down. So in this way we can animate our cube. And here is the result. So going sideways, these are A and D keys, and going backwards, this is the S key and the W key. One more final animation. These are multiple random vertices, no edges, and the observation point is moving fast forward. This was the geometry of the screen lecture, covering 2D and 3D graphics, and the next topic is the introduction to vector algebra. Thank you for watching, and goodbye.